delighted to introduce Professor Alyssa, Professor of Philosophy at UC Davis, whose research focuses on fundamentality and interpretation of quantum theories. Alyssa is the author of The World and the Wave Function, Metaphysics for Quantum Physics. I'm also very pleased to introduce Dr. Emily Qureshi-Hurst, who is a junior research fellow and college lecturer in philosophy at Oxford, whose research spans many areas: ethics, philosophy of physics, philosophy of religion, and is the author of, working on at the moment, to finish the book on God, Salvation, and the Problem of Space-Time. Congratulations.
You say the title again? God, Salvation,
and the Problem of Space-Time.
Oh, yeah.
Alyssa will be speaking to us first, followed by Emily. I'll give 9 to 10 minutes response to both papers, and hopefully after that we'll have some time for Q&A if John gives us the green light.
We'll see.
Thank you. Well, thank you so much for having me here, Emily, and for the kind invitation. So I was asked to talk about this account of how middle-sized objects come out of the wave function. If you think the wave function is fundamental and what's everything that I gave in the last chapter of my book, The World and the Wave Function. So that's what I'm going to talk about today. There'll be a lot to kind of build up to my solution because there are some problems that I need to explain, but just to kind of give an overview of the background, where I'm starting from. In this book, what I was trying to develop and defend and get clear on the arguments for was this framework for providing a metaphysical interpretation of quantum theories called wave function realism. Now there are many ways of being a realist about the wave function, but what I was interested in this book was developing this framework that's been promoted, especially by David Albert and Barry Lower, according to which any kind of quantum theory is going to be fundamentally about the wave function interpreted as a field on a high-dimensional space with the structure of a configuration space. So that framework could be applied to different quantum theories to give different, more precise ontologies. So we could look at non-relativistic versus relativistic theories. You'd have a different kind of notion of a configuration space there. You could apply wave function realism to non-hidden variables theories like collapse theories, Everettian quantum mechanics. Like I prefer, you could also apply it to hidden variables theory like Boudewijn mechanics, like David Albert likes to. Either way, you're going to take a wave function as a field in high-dimensional space to be like either all of or a lot of the fundamental ontology. So let me just, it's going to be the idea of the configuration space is going to be very, very important to the whole discussion today of the recovery of middle-sized objects. So let me just be clear what we're talking about here. So the notion of configuration space isn't special to quantum mechanics. It was developed in the 19th century to model classical systems. So like, for example, we can talk about a simple system of 2 points in a three-dimensional space. And if we want to, capture the evolution of the positions of those particles over time, we can use 2 points in a three-dimensional Cartesian space to do so. But we could also represent them using 1 point in this higher dimensional configuration space. In general, for the configuration space, it'll have 3 n dimensions, where n is the number of particles in the system. So here we're talking about 2 particles in a 3-dimensional space. If we wanted to represent that in a configuration space, we would use 1 point in 6-dimensional space. To say it's a 6-dimensional space is to say any location in that point is captured by can be captured by 6 numbers. And here the intuitive idea is like 3 of those numbers, like the first 3, will correspond to the x, y, and z coordinates of the first particle in the low-dimensional representation. And then the next 3 numbers, the next 3 dimensions will correspond to the x, y, and z coordinates for the second particle. So that's like there's a natural mapping between the representation of a location in this high-dimensional space and the locations of a system in 3 dimensions. So that's just like how configuration space representations work in a classical setting, but of course in quantum mechanics we think that particles generally don't have definite locations. Instead, you can think of them maybe somehow, if you like, as fields kind of smeared out over that space where their locations aren't definite. And in that case, when you move to the kind of higher dimensional configuration space representation, again, you're going to have something that's more smeared out like a field. And one of the arguments for wave function realism that I discuss in the book, The World of the Wave Function, because it's one of the arguments that has been used by especially Jill North and David Albert when they try to defend this way of viewing the world, is that actually it's not possible. So in the classical case, you can move back and forth between the low dimensional, the representation of the system in ordinary space and the representation of the system in configuration space. There, nobody thinks the configuration space is the real space. It's just like a convenient way of capturing the state of all these particles really simply as one point at a time and then a line over time. But in the quantum case, since we have entanglement, it isn't going to be sufficient to capture the quantum states of the system using just a representation of particles as these like independent fields in a low-dimensional space. In this case, Albert, North, and actually me too in earlier papers argued that you need these extra dimensions. Those are really enabling you to capture the relationships between the correlations between these subsystems in the lower dimensional picture. But what I want to get at today, I'm not going to get waylaid about the arguments for wave function realism. What we're trying to do here today in the short time I have is to explain, if you did think the world was fundamentally a wave function, how could you also see there being low dimensional macroscopic objects? But I'm happy to talk about the arguments in the discussion if you'd like. So here's a problem. So you might at first say like, oh, it's straightforward. If we've got this wave function in this high dimensional space, it's very straightforward to say how to recover low dimensional objects out of that. After all, I've already said, if you are, if you say, for example, the amplitude of the wave function is all clustered around this particular point in the high dimensional configuration space, we could say, well, that means that something like it's very likely we've got a system, or we've got a system that is mostly composed of individual systems that have three-dimensional locations corresponding to the location of this point in the configuration space. So if like the coordinates here of this point are, let's just call them now x1, y1, z1, x2, y2, z2, then we say that means there are two particles that are pretty much at these locations, x1, y1, z1 for the one, and the other one is at x2, y2, z2. That's the other location here. So because there's this nice mapping between the dimensions in the high dimensional configuration space that the wave function lives and the coordinates of these particles in the low dimensional space, it looks like it's going to be very straightforward to map, to find the low dimensional objects in the high dimensional ontology. But what many critics of wave function realism have pointed out is that's not the case. So they're not going to argue that there is some mapping between points in a high dimensional space and locations of a system of two or more particles in a low dimensional space. But what they're going to say is there are too many mappings. So yes, you could say, okay, I've got a particle at this point, and that maps onto some particles that have these kinds of locations where, if we're talking about a system like we observed, this point maps onto a system of particles spread out in these locations, like to make up the kinds of objects that we see here, the middle-sized objects we see here. But what Brad Monton and Tim Maudlin and others have mentioned is there are all other kinds of mappings, perverse mappings that you could do from any kind of location in this high-dimensional space to a low-dimensional ontology. And it doesn't seem right to say that all of those other weird low-dimensional ontologies are also real. So what privileges this one mapping that would take this kind of way a field would be spread out in this high-dimensional space to a system of low-dimensional objects of the kind we see? Okay, so here's a quote from, this is Tim Maudlin's 2007 paper, Completeness, Supervenience, and Ontology. He said, what the wave function monist has is just a field evolving in this very high-dimensional space, quite unlike what we take ordinary space to be, okay, this high-dimensional configuration space. It's true that under a certain fictive mapping, one can associate that evolution with the motion of local beables, meaning objects that have space-time locations or spatial locations in 3-space in an ordinary-looking space, and that motion corresponds to what we see, but under other perfectly well-defined fictive mappings, it will correspond to a bizarre evolution of local beables in ordinary space, or a bizarre evolution and a bizarre space, and so on. I call this Montan's challenge just because I found it earlier in Montan than Maudlin, but for all I know, Tim Maudlin's been complaining about this for a longer time. So the Montan's challenge, and this is like the kind of account of how we get these macroscopic low-dimensional objects out of a wave function ontology, is that I'm going to be presenting here is directly a response to this Montan, what I'm calling Montan's challenge. The challenge is what privileges the mapping that takes the coordinates of the high-dimensional space onto coordinates in a 3-dimensional space that track the locations of systems of the kind we ordinarily observe. Okay, so the first thing I guess I want to say here, just put this a little bit in context, is what I say to this problem is not the same as what David Albert has said in a series of works, like over kind of 20 years of discussing this problem, from his early 1996 paper, Elementary Quantum Metaphysics, through this paper on wave function realism, through his 2015 book, After Physics. In all of those works, he had proposed a solution to this problem that's based on a kind of functionalist understanding of 3-dimensionality. So the basic idea here, the way that he wanted to respond to this challenge from Montan and Maudlin, that, oh, well, you can map a low-dimensional ontology onto the high-dimensional ontology in all of these ways, so a mapping isn't sufficient for really getting 3-dimensional objects out, was, yeah, I know. A mere mapping isn't enough to get 3-dimensional objects out. That's not my account. What he said is, here's my account. Here's how you get 3-dimensional objects out of the wave function. I'm a functionalist about 3-dimensional objects. So I say, you have a 3-dimensional object just in case there's something that plays the causal functional role of a 3-dimensional object. And that wave function, or bits in the wave, parts of the wave function, play the causal functional role of a 3-dimensional object. So if they play the causal functional role of a 3-dimensional object, then all it is for there to be a 3-dimensional object is for there to be something that plays a causal functional role, then we thereby get a 3-dimensional ontology. And it's not because of mapping. It's not because, I mean, one thing you can pay attention to, it's about the dynamics of the wave function and about the fact that over time it's able to play this kind of causal role. It's not a synchronic fact about I can take this static wave function at a time and map it onto a 3-dimensional ontology. All right, so what is this causal functional? So here's the question. If this is going to work, Albert has to have done two things. One, he has to have convinced us that there is a certain causal functional role that's like definitive of being a 3-dimensional object. And then two, he has to convince us that the wave function or bits of the wave function ontology in this high-dimensional space are capable of actually playing that causal role. So I've been arguing for some time that he doesn't succeed in either of these in this earlier work. But let me just say briefly, and I'm sorry this is so fast, but I don't know, sorry. So this is what he says in all these papers. What he says is, if you want to know what is a causal functional role associated with 3-dimensional objects, well, the answer is it's being describable by a Hamiltonian like this. Okay. So this Hamiltonian is kind of giving us in physics, is giving us some kind of representation of how the system is going to behave dynamically over time. And in general, in classical physics, when we're talking about a system of n particle, what do I have here? Yeah, okay, I don't have it. N particles interacting over time in three-dimensional space, we can represent them according to a Hamiltonian like this that has a sum of kinetic energy terms. So the first is like 1/2 mv squared, and then a potential term. And here the potential is just written in this kind of schematic form that the way the system is going to behave over time basically depends on the interparticle locations in these three dimensions, x, y, and z, for these particles that are labeled with the i's. And so what Albert says is, in general, if you have bits of a wave function ontology that can be like plugged in here, and given these labels, then we basically have something in the wave function ontology that's playing this causal role. Okay, so that's what I already said. But there is a couple of problems with this, and actually Albert in his most recent work, so he published another book last year called A Guess at the Riddle. In the last chapter of that book, there's just 3 chapters, but the last chapter of the book, chapter 3, he says, yeah, this is not working. And it's pretty much what I've been arguing for a while, which is that, one, I mean, really that's the first thing that he's unhappy with now. The second thing, I don't know if he mentions really there, but it's the first thing. So the point is just, yes, there are many different systems that you can model given a particular mathematical representation. That doesn't necessarily mean that literally is that kind of thing. So basically the idea is, yes, we can model something using these coordinates given a Hamiltonian, a mathematical description that looks like that, but that isn't necessarily to say that we've literally got something in 3 dimensions. And so let me just leave it there. I'm happy to talk about this in more detail. But the second kind of concern that I have with this is even if we, even if we kind of said, no, when I'm writing down this Hamiltonian, I'm not just saying, am I able to put these labels on these things? But when I'm writing down this Hamiltonian, I am really describing something substantive. So I'm really just using this to say that we've got some kind of systems that are moving with certain velocities in 3 dimensions, and whose behavior over time depends on these interparticle distances that you need to recover 3 dimensions. Even if you said all that, there is nothing in the wave function ontology that is actually whose behavior is depending on 3 coordinates. And so so there are a couple of worries with this. All right, so I guess I have no idea how much time when I started, but I'm just going to keep plugging away, and you can say stop when you want me to stop.
Do you want a warning? 5, 3, 1?
Yeah.
All of the above?
5 and 1.
5 and 1.
Yeah. Thank you. Okay, so I'm concerned about the functionalism. Okay, so I'm concerned about the functionalism. I'm concerned there's nothing in the wave function. I mean, there are no privileged 3 dimensions in configuration space. I mean, that's a short story. So you've got all these, bits of wave function that are kind of evolving. You could even talk about them evolving in little 3-dimensional subspaces, and that is the picture that you have in after physics. But they're not. They're just behaving kind of over time in their own little 3-dimensional subspaces, and there's no way to link one dimension in one 3-dimensional subspace to another dimension in another 3-dimensional subspace, and so on. That's the kind of idea. So again, happy to talk about that more, but I want to now talk about what I propose instead. So I do think if you're going to be a wave function realist, it is important to respond to Montan's challenge. So I mean, you could just say that okay, fine. All you have are all these different ways of mapping the high-dimensional ontology onto the low-dimensional ontology. None of those is privileged. So yeah, there's no real sense in which there really is in the wave function 3-dimensional systems. as a, of the kind that we observe versus all these kinds of wacky three-dimensional evolutions or two-dimensional evolutions or six-dimensional evolutions and so on. You could do that, but I do not want to say that, okay? I want to say, no, we're starting from knowledge that there are middle-sized objects, three-dimensional macroscopic systems like ourselves, like our measuring devices. That's how we generate the evidence for quantum theories. We want to say that they're real, and all of these other kinds of strange things that you could get by mapping the wave function on low-dimensional ontologies are not there. So then the question is, well, then what privileges, is there any way in the high-dimensional ontology to say this low-dimensional mapping is privileged? And I think that there is. So the way that I think we can see it is going to appeal to certain kinds of dynamical invariances between quantum states. And so in physics and in quantum mechanics, when we talk about dynamical invariances, we're usually not kind of making a sharp distinction between invariances and symmetries. So we talk about system having an invariance, we're talking about symmetry, and they're kind of, these things are conflated. I'm not objecting to that, that's totally fine in physics, but for the use that I want to put this in metaphysics, it's important to kind of draw this distinction. So this is what this slide is saying. What we're going to be doing is starting from, in addressing Montan's challenge, is starting from noting that there are some kind of dynamical invariances in the high-dimensional ontology, and then we'll later talk about symmetries. Okay, so I just want to make the distinction of how I'm using these terms. And these are just terms of art here. So dynamical invariances is basically what is referred to in quantum mechanics when you want to talk about invariances or symmetries. So you have an invariance just in case the Hamiltonian commutes with the generator of the symmetry. So like, for example, if you're talking about some kind of translational symmetry, the generator would be like the momentum operator. But this doesn't matter. The point is there's a generator of the symmetry, and that allows you to transform different quantum states or different wave functions. And if it is the case that the Hamiltonian commutes with that generator, then we'll say that there's an invariance. So this just means if you took the wave function, you operated it on it with a Hamiltonian, and then you applied the generator, you would get the same thing if you took the Hamiltonian and then applied the generator and then applied the Hamiltonian after that. You get the same thing. So that's what I mean by invariance. And then I want to emphasize that we can talk about these invariances between wave functions, and that's all very abstract, and we're not talking at all about three-dimensional objects at all. It's just a fact about wave functions and how they're related to each other. But now I want to use as a separate term symmetries, and they're, when I'm saying symmetries, I'm just going to be talking about relations like if something is a reflection of something else, or something is a translation in space of something else, or something is this something else but rotated, or with some particles swapped. That's how I'm going to use the word symmetries. Okay, so let me give, this is the idea of how I think we should be responding to Montan's challenge. So start from the wave function ontology. And let's suppose that there are two wave functions, simple case, where we call one psi 1, call one psi 2, where we can understand psi 1 as psi 2 as psi 1, where we apply this generator operator to it, and we suppose that there's an invariance between these two wave functions of the kind I just described. Okay, so just suppose that that is a fact, and now suppose that there is some way of mapping these two wave functions onto low-dimensional ontologies, onto three-dimensional coordinations, such that when you do that, you see that there's some kind one's a reflection of the other, or one's a rotation of another, or one's a translation of it over in space. Okay, so they're symmetric in some way. And then suppose that if you had started with those wave functions, and instead of mapping them onto a three-dimensional ontology, you instead took those wave functions and you mapped them onto a two-dimensional ontology, or some other kind of perverse, you did some other kind of perverse mapping. And when you did that, you didn't see any kind of symmetries there. There was no interesting relation between those wave functions. Then I want to say, it would be reasonable to say the three-dimensional ontology is tracking something. Whereas that two-dimensional one, or that other perverse three-dimensional one, it's not tracking anything. Okay, so here's the example that it's like the example that I talk in my book. So, I mean, now we're just going to imagine two very highly idealized quantum states, but it's just to kind of see the argument as clearly as possible. So imagine you have these two wave functions. One is where all the amplitude of the wave function is combined to a point where the space, that high dimensional, I just put a 12-dimensional space. This 12-dimensional space is organised in such a way that we can assign these numbers to this point in the high dimensional space, and we say, for psi 1, basically all the amplitude is clustered around here. And then imagine you've got this other wave function where all the amplitude is clustered around this other point. And we suppose there's this dynamical invariance between the two in the way that I described. And now suppose if it were to be the case that you were to take those wave functions and map them in a straightforward way onto a three-dimensional ontology, you would get this, where I kind of gave up. I'm sorry, I'm not good at PowerPoint. I need a helper. These should be like smeared out a little maybe, but essentially what you get is, you get a mapping onto 4 particles. So this is the mapping when you take this quantum state and map it onto a low-dimensional ontology, and where the third dimension again is hidden. Okay, so I put zeros here so I don't have to worry about that. Okay, so this is a three-dimensional ontology representation of this. This is a three-dimensional mapping of this. And you can see, if you do that, this is just a reflection of this. And you're like, oh, that's interesting. There was this invariance between those two quantum states, and when you map them onto a low-dimensional ontology, you see that that's captured in the fact that there's this reflection here. These states are really symmetric in three-dimensional space. But then map them onto something perverse, a two-dimensional image, and so you say, like, here's the location of the first particle, here. Right, here's the location of the second particle, here, and so on. So you take these quantum states and you map them onto 2 dimensions. Now you see, look, there's no interesting relationship at all between the two. Okay, so this is like very simple, very idealized, but I'm just trying to get the flavor here. The idea is we would have reason to believe that this was a garbage low-dimensional ontology. The reason is just that kind of low-dimensional ontology isn't capturing anything that isn't already captured in the high-dimensional picture. But when we translate this into a low-dimensional image, we really are seeing something.
Right.
Okay.
Row 5.
Great, thank you. Okay, so that's a kind of response that I think is appropriate to give to Montan's challenge. The idea is Montan and Maudlin were asking us to say, what is it in virtue of which, if you have this wave function in this high dimensional space, it is also true to say there are low dimensional objects of the kind we, right? As opposed to all of these other kinds of weird things that you could get from other weird mappings. And the answer is because in this particular low-dimensional image, we find things that are reflecting this dynamical invariances in the quantum state, okay? And what we would call symmetries, asymmetries in my language. Okay, but now it's important to say that once you've answered Montan's challenge, at least in the way that I propose to, although we've explained how in a world that's fundamentally a wave function, there could also be some kind of three-dimensional reality containing low-dimensional macroscopic objects, it doesn't itself address what's been called the macro object problem. And the way I understand the macro object problem is it's demanding some kind of account of the metaphysical relationship between objects in the low-dimensional ontology and the objects in the high-dimensional ontology. Because you could still be like, okay, fine, now you've told me, like, there's a good reason to say that that three-dimensional ontology is tracking something real, but then you could say, but I can't understand how that could possibly be constituted out of a field in a high-dimensional space, where no three of those dimensions in the high-dimensional space correspond to any three dimensions in our low-dimensional space. So you have to answer that as well, but I think like we've got our foot in the door because now we're justified in claiming there are these three-dimensional objects. And so, but to answer the macroscopic, the macro object problem, what I want to say is, first of all, you know, we've got to find a kind of metaphysical relation that's appropriate. And what I do in the book is say, well, let's just use the simplest one, which is the parthood, the parthood relation. And I can't see any reason why we shouldn't view the three-dimensional particles that we've now recovered from the low-dimensional ontology, or from the high-dimensional ontology, literally as parts of the wave function. Okay, so there's nothing in kind of near...
We're down to one.
Oh, really? Okay.
1.5.
Okay, no problem. Okay, so to get the three-dimensional objects of the kind that we observe, that just gets you particles. To get the kind of macroscopic objects like us, I think you need to do more. You have to talk about their behavior over time. And I do this in a couple of stages in the book. First, by saying that we have to note the particle configurations are going to be instantiating locations, not precisely, but only to various degrees that correspond to the amplitude of the wave function at different points in the configuration space. But once you get that, then I think you're able to, you have particles that have fairly precise locations. You can just use a standard functionalist analysis that we are familiar with in ordinary metaphysics that isn't in high dimensions to recover the middle-sized objects functionally, like we usually do. Okay, I'm probably over now, but let me just, because I could bring it up, it's kind of weird not to bring it up to the present day. So as I mentioned, David Albert, in his recent book, I guess at the Riddle, does say, I don't accept this functionalist analysis anymore, so you might be curious, like, what does he say? And does he say what I want to say? And I was disappointed in reading that he agreed that his functionalist analysis doesn't work, but he didn't like what I say. And I was very surprised to find him calling me a libertine, and that it was interesting, and I was intrigued, but you might be wondering what that means.
Is it an intellectual or moral accusation? What's that?
Yeah, I mean, as a physicalist, I mean, I'm used to being called a libertine, so I thought this was going to be something like that, but that wasn't the charge. So the paradigm of a libertine position is Jonathan Schaffer, like in the ground between the gaps. So, and this is also familiar from like Levine on explanatory gaps and these various papers on the phenomenal concept strategy. So the idea is libertine in general for some kind of phenomena is going to reject a functionalist analysis and just say like from the, like in the case of the mental physical, you'd say just from knowing the physical facts, you wouldn't be able to tell that there is like consciousness there. In this case, just from looking at the high dimensional ontology, you wouldn't be able to tell there's a low dimensional ontology. What you need are these to know what the metaphysical laws are, what the grounding laws are. And then once you know those, then you can get from the physical to the mental, or from the high dimensional in this case to the low dimensional. That's Schaffer, and that's not me. So it's just, I just have to, I'm not a libertine in this sense, at least. And because what I'm doing here is saying, if you understand the behavior of the wave function over time, you can use a priori reasoning to see how an image of the world with ordinary three-dimensional objects is tracking objective structure. Right? And it's just, that doesn't come by way of a functional analysis of three-dimensionality or the misguided claim that the wave function shadows are playing the causal role of three-dimensional objects. It's coming from seeing how symmetries in a low-dimensional ontology can be tracking interesting dynamical facts about the higher dimensional ontology. And so there's no role in this picture for metaphysical laws to play. Okay, so that's it. Thank you.
Thank you.
All right, so thank you so much for having me. Just to situate myself in this interdisciplinary milieu, I'm a scholar of science and religion who approaches the interaction between science and religion from a philosophical perspective. And today I want to give a snapshot of the research project I'm currently in the middle of, in which I examine the many worlds interpretation of quantum mechanics and see whether it's a hostile or habitable environment for theism. So I began working in this area after I was invited to participate in Professor Mark Harris's Quantum Theology Beyond Copenhagen project in 2021. And my own project has sprung out of this interdisciplinary collaborative venture, and it's that project that I'll talk about today. So in effect, I'm asking, what does the many worlds interpretation mean for middle-sized creatures, i.e. human beings, and the world in which we live? So my plan today is to start off broad and offer an overview of the project and its motivations, and then I want to narrow down to a specific couple of worries for many worlds in the second part. So in the first stage of my project, I wanted to identify key problems that Everettian quantum mechanics might raise for theism. I'm specifically interested in what many worlds means for middle-sized human beings, and this is the stage that I've been working on during my JRF, and I'm coming towards the end of it. And I'm looking forward to the second stage, which I'll undertake wherever I end up next, in which I want to develop new modes of constructive engagement between the many worlds interpretation and philosophy and theology. So science and religion, the field that I work in, is pretty much exclusively focused on the Copenhagen interpretation when it's engaged with quantum physics. I think we need to move into fresh territory when it comes to interpretations of the quantum formalism. But this would only be true if there was something wrong with the Copenhagen way of doing things. So why might I be interested in breaking with tradition? The simple answer is, although Copenhagen-style approaches still dominate physics textbooks, in philosophical circles, the Copenhagen interpretation is on the decline. So Tim Maudlin is one of many people who argue that the Copenhagen interpretation should be jettisoned in favour of a more robust interpretation that satisfies the conditions for a physical theory. The Copenhagen interpretation, according to Maudlin, is no more than a vague recipe that just tells physicists to shut up and calculate. In other words, the Emperor of Copenhagen has no clothes. It fails to give a robust account of the metaphysics beneath the measurements. And as philosophers and theologians, it's the metaphysics, the type of world that we live in, that we really care about. Whether Copenhagen is right or not, and there is of course much disagreement about this, it's time to expand science and religion's horizons and focus our attention on other interpretations. We don't want to risk becoming stale and stagnant or falling behind. And I think the Everett interpretation is the perfect candidate for this, because it has the potential to really radically reconceptualize both our understanding of reality and our place within that reality. So we need to start taking it more seriously. That being said, I just want to say I'm not here to defend Everettianism today. I just want to take it at face value and explore what it might mean for theism, if it's true. So, the Everett interpretation of quantum mechanics, also called the many worlds interpretation, but not by Everett himself, emerged in a doctoral dissertation written by Everett in the 1950s. The self-proclaimed aim of this dissertation was to regard pure wave mechanics as a complete theory, and what follows is both simple and radical. Fundamentally, reality is comprised only of the wave function of the universe, and this universal wave function evolves deterministically in accordance with the Schrödinger equation. In other words, what follows is a commitment to wave function monism. Moreover, and more relevantly for our purposes today, at a quantum event, however we define such a thing, the wave function splits into branches or worlds that contain each possible outcome of the event in question and cease interacting with each other. But what does it really mean, metaphysically speaking, to say that the universe branches? A useful way of exploring this is via the famous thought experiment Schrödinger's cat. I'm sure you're all familiar with it, but I'm just going to go over it again in case. Because we're using pictures of my lovely cat Raymond, and I do sort of like him, we're going to say that the options are asleep and awake, rather than alive and dead. So, Raymond is locked in a box with a device that will break open a vial of sleeping gas if a radioactive particle decays. The likelihood of decay during the hour the experiment runs is set at 50-50. Before measurement, the Copenhagen interpretation dictates that the particle is in a superposed state of both decayed and not decayed, leading to the paradoxical conclusion that Raymond is in a superposed state of being both asleep and awake. But of course, this is a problem, because these are incompatible states. So the many worlds interpretation solves this problem by claiming that this case doesn't involve a superposed cat, rather it involves multiple, perhaps superposed worlds, some containing awake Raymonds and some containing asleep Raymonds. Whichever state of affairs we observe when we open the box indicates which world we are in, but the other worlds and their other possibilities are equally real. In effect, there are perhaps a non-denumerable infinity of worlds branching off from this one each minute, bringing new worlds and new versions of us into existence. It's pretty weird stuff. And it's worth mentioning here that there are at least two versions of Everettianism, and probably more. So one is a more conservative view, defended by David Wallace and Simon Saunders, and it sees the universe as fundamentally singular, understanding the apparent multiple worlds as patterns in one universal quantum state that emerge as it evolves in time. Key to understanding this view is the notion of decoherence, but I don't have time to go into that today. The alternative radical view sees splitting as a fundamental process. And as the radical version has the most significant implications, that's what I really want to focus my attention on. Because I think if theism can respond to the radical version, it probably won't have too much problem or trouble with the more conservative version. So my project is centered around three research questions. And they're up there. So the first question relates to personal identity. And it considers the nature of the human person and, in tandem with that, humanity's relationship with the divine. The second question relates to the concept of moral responsibility, and it concerns the role of the human being as a moral agent who must interpret and practically respond to the teachings of a particular religion during the course of their earthly life. And the third question also concerns ethics, but instead of concerning the ethical parameters of the human being, it considers the moral nature of God himself in conversation with the kind of world that we're living in. So these questions, exploring where and how middle-sized beings fit into the Everettian picture, haven't been adequately explored. And in the remaining time, I want to focus on the first and third questions. I hope to be able to cover them all, but I don't have enough time. So I want to begin with personal identity. What's the core feature of the human person without which we could not continue to exist? This question really matters. Almost all of us have the deep-seated intuition that we continue existing throughout the various epochs of our lives. Though we might colloquially say, oh, I was a different person back then, or I'm going to be a new woman moving forward. We don't really mean to say that in any serious, substantial, or metaphysically meaningful sense that the person we were in the past, or the person we will be in the future, is a different person to the person that we are now. Moreover, our profound connection with a single and unique sense of selfhood is of particular importance to the theistic understanding of the human person and that human person's relationship with the divine. Theism, specifically Christianity, doesn't really make sense if individuals can't have personal relationships with their God that are developed over the course of a lifetime. The entire notion of relationship requires ongoing, reciprocal interaction that's capable of growth and development. I need to carry on existing as the exact same person if we're able to make sense of the idea that I can have a meaningful relationship with anyone, let alone God, that persists as I persist through time. Theism also requires individuals to be justly held responsible for their actions in this life and the next. But I can't be held responsible for actions that were committed by someone else. Because philosophers really love to cause problems for even our most deeply held beliefs, personal identity has received a lot of philosophical attention over the last 2,000 years. And one of the key questions is, What conditions must hold for me to continue existing across time? There are several proposals, and broadly they can be split into psychological continuity views and bodily continuity views. Psychological continuity holds that in order for an individual to continue existing, they must be connected by a stream of consciousness or some other psychological phenomena with their past selves. And this might include having direct memories of being that past person, or indirect memories of being a past person who remembers being a past person, etc. Bodily continuity views, on the other hand, suggest that we're primarily human animals whose identity is inextricably linked with our bodies. So, how do we decide what the right way to approach personal identity is? One way philosophers have tested out which of these should be favoured is through thought experiments, and a particularly illuminating set of thought experiments are known as fission cases, originally proposed by Derek Parfit. Fission cases were inspired by cell fission, a process whereby a cell splits into two or more identical copies of itself. And the thought experiments are intended to examine whether personal identity could be preserved in such a scenario if a human being could be split in this way. Discourse on fission cases typically begins by imagining an individual splitting into two persons who seem to be exact copies, both physically and psychologically, of the pre-fission individual. So let's call a being who will undergo fission at some future time Alice, and let's call the two persons who exist after fission Lefty and Righty. The question is, after fission has taken place, is Alice identical to Lefty, Righty, both, or neither? To help us answer this, we can look to various philosophical principles. So, according to Leibniz law, if two objects are numerically identical, meaning they're one and the same object, then they must have the exact same properties. The morning star and the evening star are numerically identical because both of these names refer to the same thing, planet Venus. Moreover, identity is a transitive relation, and what this means is if Alice is identical with Lefty and Lefty is identical with Righty, then Alice must be identical with Righty. But in this case, Lefty and Righty are clearly not numerically identical with each other. Lefty and Righty have many different properties, including having distinct streams of consciousness, occupying different locations in space, they can move independently of each other, etc. So they don't share all the same properties, and so are different persons. Just by looking at them, we could come to this conclusion. And so on this basis, whether Alice can be numerically identical with either of them is problematized. Derek Parfit echoes this sentiment, saying that identity is a one-one relation that an object has only with itself, so it collapses into incoherence when fission occurs. This conclusion is not particularly problematic for most bodily continuity theorists, particularly if Alice's original body is gone. But the psychological continuity theorist faces bigger problems. They must conclude that Lefty and Righty are numerically identical with Alice because each shares psychological continuity with Alice, despite the obvious fact that Lefty and Righty are not identical with each other. Before many worlds, fission cases could have been regarded as interesting but ultimately unrealisable philosophical exercises. Brain teasers, if you will, with relatively limited real-world application. But if the Everett interpretation is right, then fission events of this kind have been part of the fabric of the world since the beginning. So what can we make of personal identity in a world in which each of us looks doomed to split into almost an infinite number of versions of us? In other words, how can we solve the problem of personal identity in many worlds? So there are a few solutions available. I'm going to have to rush through them. But the first option is to just deny that numerical identity can be preserved during fission and say that this is actually fine. So Derek Parfit argued that philosophers are mistaken in thinking that the relation of numerical identity is what's most important to us. We shouldn't ask, am I identical with some past or future person, but instead, have I survived? Identity and survival are not necessarily the same thing. Whilst identity is an all or nothing phenomenon, most of the relations important to survival admit of degrees. Moreover, all that matters for survival, i.e. psychological continuity, can be preserved during the splitting process. Physicist and passionate Everettian Sean Carroll echoes this. He argues that the idea that each of us is the exact same person from birth to death was never really more than a useful approximation anyway, so it shouldn't be too concerning that many worlds encourages us to abandon it. Carroll writes, quote, the lifespan of a person should be thought of as a branching tree with multiple individuals at any one time, rather than a single trajectory, much like a splitting amoeba, end quote. According to this view, Everettian quantum mechanics says that although there are many versions of us, each of whom can be traced back to an original person with whom all subsequent persons are psychologically continuous, we can still talk of our own survival in a meaningful sense. We do survive branching, even if we're not numerically identical with the past self afterwards. So, a couple of reflections on this. I think this probably does work on a naturalistic, atheistic worldview. The problem for the theist is that it doesn't seem robust enough to get a few different theistic commitments over the line. So numerical identity seems to me at least to be necessary for things like cultivating an ongoing relationship with God across time, and also for holding individuals morally and soteriologically responsible for their past actions. You need to be the exact same person to be held responsible for past actions. It's the height of injustice to punish an innocent person for someone else's crimes. Moreover, many theists want to think of identity as relating to or involving a soul as well as a body. The soul, however we might want to think about this, probably doesn't admit of degrees like the relation of survival does. So we need to ask, can a soul undergo branching, splitting into two souls, or an infinite number of souls that inhabit all of these additional bodies? I suspect that many theists want to resist this conclusion, and lots of them that I've talked to have been resistant to this conclusion. So my point here is that survival is not enough to get these theological commitments over the line. So we might need to look elsewhere for accounts of persistence that go further than survival and offer some kind of numerical identity. So one option of this kind is the multiple occupancy view, which claims that if there is fission in your future, then there are multiple occupants in your body up until the point that fission occurs. So before Alice undergoes fission, she actually contains both lefty and righty within her. Parfit argues that the multiple occupancy view greatly distorts the concept of a person, and for this reason it should be rejected. And I think I'm in agreement with him on this. Not only does the multiple occupancy view profoundly violate our intuitions when it appears in discussions of splitting into two, it collapses into complete absurdity in the context of Everettian quantum mechanics due to the sheer scales involved. According to many worlds, branching may well be occurring as many as an infinite number of times per second. If branching occurs as frequently as this, the multiple occupancy view is forced to claim that I contain a non-denumerable infinity of persons at any one time. And this is metaphysically curious, to say the least. And it also stretches our reasonable common sense understanding of identity beyond breaking point. So I think we would need overwhelming evidence in favour of supporting this view, and I just don't think that evidence is there at the moment. So let's move on to another option. So there is another option that avoids these problems, but unfortunately, it seems to imply that every time branching occurs, we cease to exist. This view is called the no branching view because it introduces a no branching condition into the psychological continuity view. And branching here refers to the branching of people, so yeah, not Everettian branching. So the no branching view holds that Alice's continued existence depends on any future person's psychological continuity with her, but it adds the caveat that no other being can be psychologically continuous with her. In other words, if Alice branches into two people, she ceases to exist. The post-split persons are not Alice. They're new persons who have stepped fresh into existence as Alice was destroyed by the splitting of worlds. The justification is that identity can only be a one-on-one relation between a thing and itself. But the view has a slightly weird consequence in that if just Righty had come into existence, sharing psychological continuity with Alice, then the no-branching psychological continuity theorist would say that Righty is identical with Alice and Alice has continued to exist. So one future person sharing Alice's mind is Alice. But when there are two minds, arguably meaning there's more of Alice to go around, we're forced to conclude that instead of her surviving, she's actually died. Once lefty is introduced and branching has taken place, Alice has ceased to exist. Applying no branching to many worlds leads to further counterintuitive conclusions. And actually, if it's true, then the 6-year-old child I remember being is not me and is dead. I wouldn't even be the same person who started giving this talk, despite the fact that I remember coming into the room, sitting there, beginning to speak, and I've had the continuous experience of doing so ever since. So I don't think we have particularly good reasons to accept this either. So far, I've covered a few options and not found any solutions. I think this problem remains open, and I think science and religion scholars who are interested in this area need to give the question more attention if the theistically significant notion of personal identity is to be recoverable in an Everettian context. So in the remaining time, I want to talk about the final worry for many worlds. And yeah, as I've just said, if many worlds is right, then there are many individuals with whom we share a past and not a future. So we can call these the many versions of us. If there are many Emilys, each living out various possible iterations of my life, then it must be the case that there's at least one Emily living the worst life it's possible for me to live. And there are many others living very bad lives. I think this should really matter to a creator God if such a being exists. So yeah, this relates to the problem of evil, i.e. the problem posed by evil and suffering to the existence of a creator God who knows, sees and can prevent evil, but seems to allow it in at least some cases. When considering the implications of scientific theories on middle-sized objects, the problem of evil frequently raises its ugly head. And as you'll no doubt know, the problem of evil is the oldest and most frequently cited argument against the existence of God. So for this reason, we could fill entire libraries with the literature written on it. I'm just going to go over it really, really briefly. So the problem of evil holds that evil and suffering presents a significant challenge to the existence of the God of classical theism. Why? Because if God is omniscient, then God is aware of all instances of evil. If God is omnipotent, then God could stop all instances of evil. And if God is all-loving, then God should want to stop all instances of evil. But a mere glance around the world tells you that evil does exist. So some further explanation is required. I want to argue that Many Worlds raises both a new and an enlarged version of the problem of evil. So the enlarged problem involves claims about the significantly larger amount of evil in an Everettian multiverse, and the new version of the problem is that God chose laws of physics that seem to entail certain types of suffering that seem contingent on other universe models and necessary on many worlds. So I'll start by setting out the enlarged version in dialogue with Marilyn McCord-Adams and Stuart Sutherland. So they define a particularly problematic set of evils, which they call horrendous evils. And these are, quote, evils, the participation in, i.e. the doing or suffering of which, gives one reason, prima facie, to doubt whether one's life could, given their inclusion in it, be a great good to one on the whole. Such reasonable doubt arises because it's so difficult humanly to conceive of how such evils could be overcome. Because these evils are so overwhelming that they make you doubt whether your life was worth living, it does matter whether one of your futures contains horrendous evils or not. And this is where Many Worlds comes in. Over time, the various world branches will end up evolving in different directions, bringing real-world differences to the lives of the middle-sized inhabitants. If there are an infinite number of world branches, it's reasonable to suppose that the lives of some of them contain horrendous evils. And if this is true, then the Everettian multiverse contains far more suffering than an ordinary universe. And clearly, this is a very bad thing. Now, if you're an optimistic theist, you might make the following response. You might say, okay, there is much more suffering in the many worlds of Everettian quantum mechanics, but there's a correspondingly greater amount of good. For every suffering version of me, there's at least one version living the best life, and countless more living very good ones. So on balance, the distribution of good to evil isn't so unlike the world described by non-Everettian physics. So they might claim the problem of evil isn't actually any greater than it was before. But I think this response fails. And I think it fails because it doesn't recognise an important distinction between two equally important descriptions of God, both of which are pointed out by Adams and Sutherland. So the first is that God is a provider of global goods. But the second is that God is a loving parent of each individual person. Generic global responses to evil, such as those that highlight the distribution of evil on a large scale, only recognise that first, rather more detached depiction of God's nature. As a provider of global goods, we might understand how God could choose a design that vastly increases the number of people who are able to live joyful, fulfilling, happy lives. But, as a loving parent, it's very hard to understand why God would create a cosmos in which at least one version of every single person is living the worst iteration of that life possible. In effect, I'm arguing that any response that focuses on a global distribution of goods and evils ignores the plight of those individual persons who suffer greatly, recognising only one aspect of the divine nature. And joy and suffering are not morally equal. I think this is really important to note as well. If we encounter someone being tortured, suffering immensely, while the torturer is experiencing an exactly equal amount of happiness or pleasure, our moral intuitions tell us that we should stop the suffering. As such, the benefits befalling some versions of me in the Everettian multiverse are vastly outweighed by the price that other versions have to pay. And so for this reason, I think that the many worlds interpretation potentially increases the amount of evil, and this is a problem that needs a response. But if that doesn't convince the optimistic theist, I have another point. So I also want to argue that many worlds raises the problem of evil in a new way. So from the very structure of the Everettian multiverse, it seems like suffering follows necessarily. It's no longer a contingent matter whether one's future will contain horrendous evils, extreme suffering, or be negative. Somewhere in the Everettian multiverse, there will be versions of you experiencing these things. Moreover, traditionally reached for theodicies that place the blame for evil with humanity and original sin can't work here, because the suffering is woven into the very fabric of the cosmos. And I think this is a slightly new iteration of the problem of evil. If Everett was right about how to interpret quantum mechanics, it seems as though God chose to instantiate a particularly cruel set of physical laws that makes suffering emerge a necessity. Early pioneer of science and religion, Robert John Russell, calls this type of argument a cosmic theodicy because it concerns the very nature of the cosmos or the universe itself. Russell argues that those who deny divine responsibility for evils that follow directly from physical laws elevate the problem of evil to one of cosmology. But according to Russell, this response is doomed to fail for anyone who wants to claim that God is omnipotent. God, as omnipotent creator, must have had radically free choice over the fundamentals of nature, including, of course, the laws of quantum physics. So an omnipotent God could have created another type of universe altogether, in which the cruelties of our own may have been avoided. So for that reason, cosmic theodicies don't solve any problems. Instead, they just push those problems back one step. Although God isn't directly responsible for individual instances of suffering, God is indirectly responsible insofar as God created the features of the universe which cause that suffering. So I think we do have a new dimension of the problem of evil which requires a fresh and directed response.
We have about 2 minutes.
I'm almost
Oh,
done.
wow.
So yeah, just to briefly sum up, I hope to have given a brief indication of some of the problems the radical version of the many worlds interpretation raises for middle-sized objects in the context of theism. Thank you.
Thank you both very much. I'll begin with Alyssa's paper. I'd first like to say how much I enjoyed reading The World in the Wave Function, which is both a philosophically serious and yet very accessible discussion of important issues in the interpretation of quantum mechanics. As you've heard, there's a sustained argument for why we should think of the wave function of quantum mechanics as a high-dimensional physical field. To recapitulate, the challenge for wave function realists is to account for how the three-dimensional world of scientific observation, which includes the middle-sized things to scientists, is supposed to emerge from this high-dimensional field. And Alyssa proposes this two-step approach to recovering these middle-sized macro objects. The first involves the grounding of three-dimensional particles in the high-dimensional wave function field by appealing to certain symmetry considerations. And the second step involves the functional reduction of macro objects to these microscopic particles. I want to focus on the first step. So the microscopic particles that play the functional roles of these macroscopic objects are said to be real but derivative. They're constituted by the high-dimensional field. When asked to admit a non-eliminative grounding relation between the high-dimensional field and the three-dimensional micro-objects, and we're told that this is a mereological relationship in which the particles count as parts of the field. So my worry is that these particles are not being grounded in the field in a principled way. And I'll try and break this down into a couple of points which may simply represent misunderstandings on my part. Clarify. First, grounding is supposed to be a necessitation relation, but it still seems to me, in spite of what Alyssa said, that the same wave function field could be associated with a different set of objects in these three-dimensional micro-objects. As Brad Monton has pointed out, and as Alyssa has acknowledged, the high-dimensional space of the wave function does not possess of itself any structure, indicating how its points should map onto three-dimensional particle configurations, nor is there anything in its structure to suggest its dimensions should be grouped in threes. In response to Monton's challenge, Alyssa claims permutation symmetries of quantum mechanics provide a dynamical reason for preferring certain decompositions of the high-dimensional space. Specifically, the laws of the high-dimensional wave function remain invariant when we permute the particles in the three-dimensional representation. As Valia-Allery complains, however, this seems to get the order of explanation the wrong way round. The reason this invariance in the laws of the high-dimensional space exists is because of the symmetry we observe in the three-dimensional system that is reflected in the Hamiltonian that we use to characterize its dynamics. If we thought of the wave function thought of the wave function as being a physical field in the high-dimensional space, however, then it seems we would have to relinquish the idea that symmetries are a guide to ontology. So it's been argued that a wave function field doesn't transform in the right way to preserve Galilean invariance or time reversal invariance, for instance. So it seems, and I may be misunderstanding something, there's a strange inconsistency in requiring symmetries to play a fundamental role in justifying the grounding relationship between the field and the particles, whilst refusing to take symmetry as a guide to the fundamental ontology. So I'm worried that what you're giving with one hand, you're taking back with the other. But that may be a misunderstanding. Secondly, it's unclear to me that the micro-objects in the wave function field possess the right kind of properties to be mereologically related. So ordinarily, if x is a part of y, then the intrinsic properties of x and y should be determinants of the same set of determinables. But that doesn't seem to be the case here. The particles are supposed to be mereological parts of the wave function field, and yet they are essentially three-dimensional objects following trajectories in three-dimensional space. They're not located in the high-dimensional space of the wave function field. Now, it occurs to me that there could be a way for panpsychists like Philip Goff to fix this problem, elaborating on a suggestion made by Mario Hubert, who observes that we do not think of thoughts as having specific locations in our brains. So according to cosmopsychists, the cosmos as a whole instantiates mental properties, so they might conceive the three-dimensional particles as being representations of the high-dimensional field in a cosmic mind. In this sense, the particle configuration could be a part of the physical field, but the particles would not have to be located anywhere in the high-dimensional space of the wave function. In this picture, the three-dimensional particles would not be grounded in the purely physical properties of the high-dimensional field, but in its psychophysical properties, if you like, and then I think my objection would disappear. But of course, such a move would compromise the second step in our model, which invokes functionalism to account for all the properties of macro objects, including presumably mental properties. But it seems philosophers would have fun with that, so I thought I'd just mention it. Although wave function realism is supposed to be consistent with different interpretations of quantum mechanics, Alyssa has expressed a sympathy for the Everettian interpretation. So I'd like to change registers now to comment on Emily's paper, which highlights some of the difficulties Everettianism poses to theism, especially Christian theism, I think. I thought this was a very interesting way of probing the ontological implications of Everettianism. I look forward very much to seeing how the project develops. Given the interdisciplinary nature of our gathering, however, I thought it would be helpful to raise a couple of methodological points for clarification before we all start arguing about the very interesting metaphysics of the discussion. First, suppose physicists are converging upon the Everettian interpretation. I don't have the statistics. Even so, some people may be wondering why you think theologians should feel compelled to make Christian theism Everettian compliant. Do you think theologians should construct an Everettian theology because you're convinced this interpretation is probably true? Or do you think this is just where things are going in the scientific community and theologians need to get on board? Or maybe the goal is to get Everettians to come to Evensong, which is 6 p.m. I raise this point because, of course, there are many factors involved in constructing and judging rival interpretations of physical theories, as you know, including the kinds of epistemic virtues people think they ought to embody and how these virtues ought to be ranked. And there's some people in the room, the McIntyre like Daniel DeHaan back there, who are going to question, I think, whether there is a standard that experts can reasonably hope to converge upon, which is independent of the philosophical or theological tradition in which they are practicing, and maybe other sociological considerations. So if more physicists are becoming sympathetic to the Everettian interpretation, that might reflect a sociologically interesting fact about how they're being enculturated from this perspective, but it wouldn't necessarily constitute a reason for theologians to strive for Everettian compliance. Perhaps it's the Everettians who need to be evangelized. My second related point concerns the theoretical costs involved in the project of adapting Christian theism to make it consistent with the Everettian interpretation. I suppose I'd like to know a little bit more about the project's criteria for success or failure. Could one reach a point of crisis in this process of adaptation in which one is adding too many disciples, so to speak, to Christian theism to make it tenable? Might one reach the stage of acknowledging that one's no longer thinking about theism in a distinctively Christian way? One of the concerns you've expressed for Christian theism centers on the notion of there being persistent persons to whom the Christian God, who is love, relates in a loving way. But there are, as you know, atheitic forms of theism in which the distinction between individuals and the divine dissolves within a boundless subjectivity, and perhaps these alternative forms of theism fit better than Christian theism with an Everettian way of thinking about quantum mechanics. If so, would that count as a reason for Christian theists to reject Everettianism and put forward some other interpretation of quantum mechanics, rather than seeking to make their theology Everettian compliant? Underlying both of those questions, I think, is a suspicion that the data which you're bringing to theology for consideration has been predigested philosophically. Mark Harris, I think, expressed a doubt yesterday about whether one needs a philosophical system. My worry is that if theologians try to construct a theology of science without settling philosophically where the goalposts of an intelligible interpretation are to be found, they might end up playing somebody else's game. If one's theology of science were freighted with a pre-Christian Aristotelian philosophy of nature, however, the kind of what Koons has been sharing with us, which isn't so far from what was widely assumed by many Christian, Jewish, and Muslim theologians in the Middle Ages, I wonder whether the task of understanding theism in relation to an Aristotelian Everettian interpretation might look rather different, and whether it would afford better prospects for Christian theism. That's what I wanted to say.
So, with that being said, we are going to reintroduce William Simpson to the chair.
Yes, we're just going to have the speakers have a chance to respond to some of the comments I made, and then we'll just go straight into Q&A until 2 o'clock, is it?
I think we'll lead with 5 minutes, so we will have 20 minutes of discussion. So we will have one back 15 minutes. Yeah.
Whoever wants to go first.
Yeah, so thank you. Those are really, really great criticisms that the first one I need to think more about. So I wasn't trying to, when I talked about the particle relation and claiming that the wave function is the whole, and the particles are the parts, even though they're in different spaces. I did want to, I guess the first and your third criticism were both about that. So I wasn't trying to say that was a grounding relation. I was just trying to say, so I think in general when we talk about, we make a particle relation, we don't necessarily say what the grounding relation is. I mean, this is what I take one of the things like Jonathan Schaffer kind of showed us. You could be, because you could be a priority pluralist, you could be a priority monist, and so just by saying there's this part-whole relationship, there could still be leftover questions about grounding. But this issue about should there at least be necessitation, yeah, I want to think about that. I was thinking, yeah, I just don't know, because I wasn't trying to capture
So
grounding
a feature
relation.
of the Fine program of grounding is that there should be a necessitation.
I'm not, but that's fine, but I'm only claiming a mereological relationship here. I wasn't claiming a grounding relationship,
Okay.
just by, I didn't say that the mereological relationship was grounding, I said it was a metaphysical relationship between the two. So you could just say, okay, you've got this ontology and you've got this ontology, what's the relationship between the two? And I'm just starting from saying it's a part-whole, there is a part-whole relationship. Now whether or not that means that, that tells you, I'm not saying that the mereological relationship itself is a grounding relation.
Okay, but the whole that we're talking about here is the physical field.
Yeah, the
And
wave
parts
function.
that we're talking about here are these three-dimensional particles.
Yes,
And
I do believe there's a grounding relationship between those two,
right.
but it's not completely captured by the fact that there's a mereological relationship between the two.
Okay.
So, but yeah, I mean, I want to thank you for like engaging with this and raising this question about where.
It seems like something more needs to be said in order for
where
there to
the
be a grounding,
necessitation.
if you want it.
Yeah, and I don't think that a mereological relationship is a grounding relationship. I mean, it's not just Jonathan, like I think many people have pointed, Elizabeth Lawrence has a paper on emergence where she makes this point also. But yeah, good. But thanks for pressing me on this. I mean, I was trying to be provocative at that point of the book, and I wanted people to fight me on that. So we can talk about like, yeah, is this okay to call this a mereological relationship, even though they're in two different spaces? And I didn't see why, wasn't seeing anything in the mereology literature to say you couldn't do this. But then the other point you had was something about the determinate. There should be a determinate determinable.
Yeah, I suggested, and maybe someone will contradict me, that X is a part of Y, and the intrinsic properties of X and Y should be determinants of the same set of determinants.
Oh, okay. The intrinsic properties should be, okay. Okay, well, I'll write that down. I have to think about that. I guess I wasn't thinking about that. I never thought that was the case, but maybe I can be convinced, so. Thank you. And then the thing about symmetry, so I did want to talk about, that is something that Thalia has pressed me on for a while whenever we talk about this, and I'm happy to bring this up. So I don't think, I think what's happening here is just that maybe you and Thalia don't like how I say there are symmetries here, and you want the fundamental on top. So, okay. So it just is going to be the case that in a situation where you have one of these symmetries in the three-dimensional ontology, there are multiple wave functions. And so you could complain, as I think she does, and well, other people have complained that there's not, you don't have any kind of, you have too many wave functions. There shouldn't be so many wave functions here. There shouldn't be a distinction between the wave function where the particles are here and one where they're here. And so at least this is what, so we have too much structure in the wave function ontology. I want to deny that. So the way I'm looking at things is we've got some other arguments that I just didn't talk about today, because I didn't just read my whole book. But there are several arguments for the wave function view. The wave function realism, those motivate you to think the reality is this higher dimensional space wave function. And now it's going to turn out that there are, lots of wave functions, maybe too many than some people would want. But that doesn't mean I've taken away symmetries, because there are these interesting relationships between wave functions, and that's what it means to say there's a symmetry. it means that there are these commutation relations, and I'm not denying that there are these commutation relations. Now we wind up seeing these, and they're interesting to us and important when we look at the low-dimensional image that's generated from them, where there are these interesting relationships of reflections and rotations and so on. That's where you really see the symmetries manifesting. But I don't think I'm not rejecting them. I'm just, So that's really all. But yeah, we can talk about this more.
Okay, thank you very much.
Okay, I'll just briefly respond as well. So I really appreciated the methodological questions. I think those questions are very interesting. And as for, physicists converge on Everettianism, should theologians follow suit? I think it really depends on your own particular commitments, what your epistemic starting points are, and whether you think science and theology are more fundamental. So if and to the extent that science and theology might come into conflict, which one do you believe with a greater degree of certainty, or which one do you see as the more grounding aspect of your worldview? And that will inform the extent to which you think that theologians should follow. But I think if we look back over the history of the interactions between science and religion, we see this kind of thing happening a lot. So we see particular religious ideas being challenged by science, and then really interesting, intricate, beautiful theologies coming out in response. So thinking about Darwinian evolution, for example, that challenged the idea that species were created in their final forms. And then we've had some fantastic theological reflections on the basis of that later. So I think theology and religion is often and always doing this, if it wants to be outward facing and if it wants to have porous boundaries, which I think that it ought to. Especially if you are a theist and you believe that God created the world and God wrote the scriptures, then you should think there should be some sort of resonance between those two. So I think theology is at its best when it's outward facing, when it's engaging with science, and when science is able to encourage theology to maybe look at some of its views again.
That's helpful. Do you see any sort of mediating role for philosophy, say, for natural philosophy, not something specifically theological?
Yeah, and I think...
Professor Swinburne, can you hear what's going on up here?
I can, but I only just come in, so.
Okay. Well, if you'd like, there's also seats closer if you'd like to come closer.
All right. Well, thank you.
Yeah, well, I think it's difficult for science and theology to talk to each other until they're translated into the language of philosophy. So I think philosophy can be a mediating force between them, and it can also be the common language into which you translate them both and then do some philosophical work. That's the kind of thing that I'm interested in doing. And it's not the only approach, but I think that it depends how we define science and religion. I don't want to get into that too much, but...
No, that's helpful. I think what I was like, thicker conception of natural philosophy than you do.
Yeah, okay, yeah, let's open up to Q&A. I can talk for ages about that. What can I do too?
Yeah, I wanted to press, I think it's a version of William's order of explanation worry.
Okay.
So, you mentioned decoherence, but it plays an important role in giving you the localized particles,
Yeah.
right? And that depends upon, in practice, on very specialized thermodynamic and chemical and other kind of middle-sized object constraints, right? Which then explain, I think, why the wave function has the very complicated Hamiltonian it does, right? So if that's right, then it looks like to try to build the middle-sized world out of the Hamiltonian is sort of going, I don't know, the wrong direction, right? I mean, the Hamiltonian is what it is because the middle-sized world is the way it is, right? Especially, well, anyway, so that's the word, I guess.
So this is a question that I feel like Howard had asked to George and you in the first section, that I guess I feel like I'm missing something. I agree that the reason why, it's interactions with macroscopic systems that's in general getting you decoherence, but I don't see why the descriptions of those systems can't be given in completely microscopic terms. And so I don't, like, it's not that I disagree with you that in the explanation middle-sized objects are playing a crucial role. I just don't see how that challenges the kind of reductionism that I'm defending.
Yeah, so it'll force me to fall back on the other arguments I'm trying to give about the irreducibility of the thermodynamic and chemical properties. So if they're fully natural fundamental properties, then of course,
Yeah, unless I'm missing, like, I really feel like I'm missing something, like, in that, because, and Howard is too, I think, if we're, so maybe we should keep talking about it, but I think that's the, maybe,
Sam is a finger allowed.
Yeah, yeah.
I mean, epistemological priority doesn't mean ontological priority.
Exactly. Yeah.
And a thing can be natural without being fundamental on this picture.
Yeah.
I think you seem to think, well, if it's natural, it must be fundamental. If it must be fundamental, it must have its own causal role in addition to anything else. So if the top level has that, it must be influencing things down. Otherwise, it would just float on top of what's happening. And I think you're objecting, and I would object, epistemological priority isn't a guarantee of anything in these cases.
Yeah.
Finger on that. Isn't Rob also holding like this timing constraint? That's also part of the feature, and because of parsimonious view of ontological objects, and so you don't want like duplication, over-determination of these things doing more things than they are, and he doesn't think the causal work can be taken over by the lower level things.
That's what we're disputing.
Yeah, right.
So, so I don't know, the picture that I'm thinking ontologically is the microscopic, is the fundamental here, but, and then you can explain I think everything, at least in terms of decoherence, can be given that kind of description.
So I guess I don't think it's an epistemological priority then,
Okay.
and that my intuition is giving me. It's that there's a metaphysical explanation here as to why the Hamiltonian looks the way it does in terms of middle-sized features.
Yeah, okay. Yeah, then I want to see the arguments more, and but that's fair enough.
Philip, was that a new question or a follow-up? New question. So you're in the queue, I'm afraid.
Yeah.
You're next.
Yeah, I'd like to ask Emily, I can't quite say whether this is sort of vaguely Kantian question or not, but is there a reason to think of branching in terms of fission? Basically, I want to challenge the idea that fission is a good way of thinking of branching, because the thought experiment about fission is about something that happens within the world, whereas branching clearly isn't. And I wonder then if one needs to be rather more careful about one's terms, mind, psychological continuity, body, in order to apply this thought experiment for something that in fact does not happen, to something that apparently is happening all the time. And I wonder if that gets at the sort of the Kantian thing, I suppose, maybe not quite, is the sense that we are illicitly taking over intuitions from our experience to an ontology which clearly completely exceeds or cannot be captured by our experience. And therefore, presumably, we have no reason to think that it will answer appropriately to our intuitions. I wonder what you think about that.
So I think I'll start with the second part first. I think it may well be the case that our intuitions just can't really get us very far in instances of branching. But then, then we're just cutting ourselves off at the knees. We're stopping the work before it's even started. So I want to resist that just to see how far that we can get, even if ultimately maybe it is the case that we won't be able to get particularly far because our intuitions and our experiences are so restricted by, if we are experiencing within one branch rather than there being lots. And the reason I think fission might be useful, I don't think that it's exactly the same, the type of branching we're talking about in FIT and quantum mechanics and the type of branching that happens in fission, but I think it's a useful thought experiment, and the things that I'm interested in occur in both. So an individual, and then there being multiple individuals in the future. on the particular version of Everettianism that I was engaging with. I mean, we probably don't have time to talk about all of the different ways we would take that.
My question would be whether one and multiple even really mean the same thing, where we're talking about multiplicity in terms of branching versus multiplicity within. That's, I think, might go even deeper than it seems. Perhaps it's clear what she's for.
No, thank you.
So Christopher Oldfield?
Hi. Thank you both of you. I have a question for Alyssa. And I suppose you addressed Monton's challenge, right?
Yeah, I call it Monton's
challenge.
challenge.
And I'm wondering if Monton's challenge is slightly different. I wonder what you think about this. So let's take Monton's challenge to be, how do you recover a three-dimensional analysis from a five-dimensional analysis where there's multiple dimensions in a configuration space, something like that? And I would take Morden's challenge to be something more about the manifest image, scientific image difference. So Morden, as I understood him, in maybe the workshop that became your green book, I heard him once say there's a really significant choice point, and it was about the demands you make on the physical theory. So he said, take Newton's theory. No one ever tells you what a body is. It just says everybody seems to be in a right line. It doesn't tell you what the right line is, it doesn't tell you what a body is. It sort of assumes, it takes for granted that someone can go, one of them. And I wonder if there's a different challenge implicit in Morden's worry to, say, the Bouverie or the Everettian. Whatever happened to your tables and chairs and the sorts of objects you can pick up in a manifest image? I don't think that's obviously the same. It's quite related to the same as Monton's challenge for how do you basically embed a three-dimensional analysis in a high-dimensional analysis. But I wonder, could you just, what do you think of that? That there might be two different challenges here? Or am I just missing something?
There are many, but so I was just describing the problem that Maudlin was raising in that quote that I had.
Yeah.
So, yeah, I mean, there was no workshop that led to the Green Book, but like he's raised like many different objections to wave function realism. So, did you want to? But
it might have been.
This is the challenge in the quote.
Yeah.
Was identical to another challenge that Monton raises in one of his many papers criticizing wave function realism. So I'm happy, can you tell me, I don't know, did you want to raise a different problem and ask what I say about it, or? Because if you're just saying like, there are different things that Maudlin says, I totally agree. Yeah.
I think we'll have to close down.
I'll think about that.
Okay.
On to the next session, sadly, press for time. So.
That was our 20 minutes, I'm sorry.
Thank you so much.